I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Good evening, everyone. Welcome to Wonderfest. My name is Tucker Hyatt. I'm the founding director of this Bay Area beacon of science, this oh so small, in fact, maybe the world's smallest nonprofit. Small but mighty, and it's mighty because you are here. Thank you for being here. Tonight's Wonderfest speaker is Dr. Raphael Bousso, professor of physics and holder of the Chancellor's Chair in Physics at UC Berkeley. The holder of the chair, perhaps he's the sitter-in of the chair as well, but he enjoys the Chancellor's Chair. Raphael earned his PhD at Cambridge University, where his doctoral advisor was a certain Stephen Hawking. Dr. Bousso then did research at Stanford, at the Kavli Institute in Santa Barbara, and at Harvard and Radcliffe. Raphael has a delightful willingness to apply his deep physics understanding to broad questions. Back in 2004, for Wonderfest, he addressed, "Do we understand time?" Yikes. And in 2006, he tackled, "Is the world made of strings?" That strings talk was a dialogue, and Raphael's dialogue partner was a string theory pioneer, Leonard Susskind. I need to tell you something new about Lenny. I got to call him Lenny because we had a conversation, and he assured me that's all right. Raphael and Lenny are friends, and the Wonderfest Board of Directors has just awarded Leonard Susskind the Carl Sagan Prize for Science Popularization. So a good buddy of tonight's speaker, a colleague of tonight's speaker, is getting a very nice award from Wonderfest. I'm glad about that. Okay. In 2011, Bousso and Susskind co-authored a paper that highlights their mutual willingness to take on big questions. Its still famous title is The Multiverse Interpretation of Quantum Mechanics. Now, the word multiverse there doesn't seem like it quite belongs. Maybe instead we're used to hearing about the many worlds interpretation of quantum mechanics. The word multiverse was heard here just a year ago when Alex Filipenko, professor of astronomy from UC Berkeley, go Bears, came to tell us about our understanding, our hypothesis that the multiverse, many universes exist. And he gave a great talk about that. That's how this title uses the term multiverse. Not the many worlds of quantum mechanics necessarily, but rather the multiverse of the cosmic multiverse, as opposed to the quantum multiverse. And this wonderful paper by Bousso and Susskind was entitled The Multiverse Interpretation of Quantum Mechanics, bringing these two infinities, these two, or maybe they're finite, but these two enormous concepts together, saying that we could best understand the universes if we brought the cosmic multiverse and the many worlds of quantum mechanics together. That's what that paper tried to do. And I'm not qualified to say whether it succeeded, but it's still highly cited. Now, I want to mention Susskind for one more reason. Lenny Susskind, I recall saying somewhere that he said the laws of physics are the rules of reality. And I'm a physics teacher, a high school teacher for 33 years. I love that notion that that's how important physics is. It's the rules of reality. And so when I invited Dr. Bousso to speak tonight, I asked if he might work the word reality into the title of his talk. And he gave it a good thought, he tried, and then he reported, no, he came up with a great title like Gravity as a Quantum Computer, but alas, he said, here's the title, Sorry, No Reality. I have a feeling there'll be some reality tonight, if not in the title. So please welcome to discuss the reality of gravity as a quantum computer, UC Berkeley physics professor, Dr. Raphael Bousso.
Thanks so much for being here. Is that about good? Thanks for coming, and it's an honor to be back at Wonderfest. I hope you support the organization. Tucker is fighting the good fight, making the world a better place. And every 20 years, he invites me to be part of that. Actually, now that we started with reality, maybe I should just use that as a hook. The reason I resisted the word reality in the title, and I have to apologize, I'm a little hoarse, so there'll be the occasional drink stop. Yeah, so when people ask, is this or that real, often associated with scientific concepts, I find that that's a meaningless question, and one that ends up undermining, if we as scientists say, this or that theory we have right now, that's reality, this is it's the final word, we're setting ourselves up. That never happened in the history of science. That's not what science is about. It's about, and I'm speaking now from the perspective of a physical scientist, of a physicist, it's about better and better approximations, more and more general ones, coming up with concepts that encompass more and more of the world. And it's this concept of unification which will run through this entire talk. Unification means a couple of things that, at least in the history of how physics has played out, have always come together. It means that we describe more things with fewer ingredients and more accurately. Okay? So a great example of that is the Newtonian revolution, when we were able to describe more things, both heavenly and earthly things, celestial and terrestrial phenomena, with the same idea of a gravitational force, why the apple falls, how the planets move, completely mind-blowing at the time that those things have something to do with each other, but also more accurately, right? So before that, the state of the art was Kepler's laws. Every planet was assigned some sort of ellipse that it had to go around, and that's a pretty good approximation. But it doesn't explain how the apple falls. And it's actually not as accurate as Newton's laws. Newton's laws allow you to compute all sorts of corrections to the elliptical. First of all, they allow you to recover Kepler's idea. If you actually calculate what the force does, you come up that, to a pretty good approximation, it'll make the planets move in elliptical orbits. And that's great. But that's just the force of the sun on the planet, on each planet separately. Then, of course, the planets, they have gravitational attraction between them too. This is most noticeable with the big ones like Jupiter and Saturn. And those mutual tugs, they change these ellipses a little bit. And so they don't exactly have that shape. And you can calculate this and you can check, and people had in fact done accurate enough observations even at the time that you could see that these corrections were in fact a better match to the observations. So I want you to keep that in mind as my definition of progress and of unification in physics. It's not that we claim at any one moment that we have the reality. It means that we're able to see more things through a single lens, and we're able to describe them more accurately. Okay. And I should say, please interrupt me with questions, especially clarification questions. Anything with like a very long discussion, I would probably defer to the end of the talk. But I'm happy to make this a little more interactive. Yes.
Oh, sorry. I just wanted to know whether or not having a parsimonious, elegant explanation is the goal. Well, why is that the goal?
Oh, that's a great question. Yeah. Why do we feel?
Necessarily,
yeah. Well, I left out number 4.
Correlate with reality.
So, and number 4 is, ultimately why for most of humanity we were paid. Number 4 is that a theory with fewer ingredients that explains more phenomena is more predictive. It is better at telling you what happens next. And I mean, the accuracy is sort of obvious, right? I mean, we actually need general relativity as an improvement on Newton's theory of gravity to like make GPS work, because otherwise, we'd be off by a few meters here and there. And but more generally, imagine if I just had a list of facts, of observations. I saw the sun over here one day and the moon over there, and I saw the apple fall, and I just keep writing that down in my notebook, and I never do anything with it. That's sort of the caricature of no unification at all. Okay, and you can see how that makes absolutely no predictions at all. Right? Yeah.
Systematization.
Yeah. So predictions turn out to be useful, from like agriculture in ancient times to, all sorts of technologies today. And that's, I mean, to me this sounds like a very unpoetic way of valuing progress in science, but it's tangible, and that's sometimes useful. All right, so I want to kind of do a quick summary of, a very brief summary of the history of unification of progress in physics, with a very, very biased viewpoint towards, focused almost entirely on gravity and of course somewhat on quantum mechanics. Why? Because today, these theories which sort of were formulated, quantum mechanics, I think, was put in its final form about almost exactly 100 years ago, like maybe today or something. And general relativity is 10 years older than that. So these theories have been around about 100 years. And they are the last remaining two frameworks, major frameworks in physics, that have not been brought under one roof. And there are asterisks here. You can bring them under one roof in some hypothetical universes that we don't happen to live in, but in which you can ask already some interesting questions about the consequences of that kind of unification. So it's not like we've achieved nothing in these 100 years, but it's been by far the most difficult problem in the history of physics, especially considering how many people are working on it and what sort of effort has gone into it. Let me go all the way back before we get to quantum mechanics and quantum gravity and how we might do that, and start with gravity in ancient times. But I do want to give away a punchline, just so you know where this is going. Where this is going is that what we've learned, certainly very dramatically during the time that I've been active in physics, is that this particular unification step that we're going to do next is going to be quite different from everything that's come before in its very nature, and that in fact we've discovered that gravity already knows something about quantum mechanics, even the allegedly classical, not at all quantum mechanical theory that Einstein wrote down. So going all the way back, I would say the study of gravity began in ancient times with the study of planetary motions, and generally the motions of objects in the sky, but the planets were maybe the richest phenomena that people could observe. Of course, they had absolutely no idea that they were studying gravity. The idea that there's a gravitational force and that the planet's motions are governed mainly by that force, as I said, came only with Newton thousands of years later. But you could see these things in the sky moving very different from most of the bright objects, the fixed stars, being in front of different constellations at different times and so on, and moving relative to each other. And of course, there was also the moon and the sun and so on. And it would be nice to have a nice description of that, maybe because it seems intrinsically interesting, maybe because it lets you keep better track of the seasons or something, and that's always useful. And so people, wrote things down in their notebooks or whatever they had at the time, chisel things, I don't know. and try to discern patterns, right? And the Ptolemaic system that grew out of that was actually, you know, it has a terrible reputation because of its deference and epicycles and equants and whatever things they had. And it looks horribly complicated, and it was unnecessarily complicated, but not for some valid reasons you could complain about it. But the main reason why people complain about it is that it put the Earth in the center, and that's actually not a terribly valid reason. I mean, first of all, we make our observations from there, so it's all, you know, nice and wonderful that we know that it's somehow fundamentally simpler to think of the planets as going around the sun in some sense. But first of all, the sun isn't really in the center. It's like in the focal point of these ellipses, which is a little off. And secondly, it's just a matter of perspective. At the end of the day, what matters is if you can account for the observations in your notebook. And frankly, knowing, you know, how the Earth goes in an ellipse around the sun, you actually have to like work your way towards like your notebook from that. Oh, here's how the Earth moves, and here's how, I don't know, Jupiter moves, and now I have to like calculate the relative motion of Jupiter to the Earth from this very simple viewpoint, but in terms of the observations I make, the simple viewpoint is far from them. So they were, the thing that was not nice about the Ptolemaic system is that because it didn't understand the preferred role of the sun as the main source of gravity in the solar system, it was what we now call fine-tuned. There were ingredients in this complicated calculation of the orbits of each planet, which, you know, basically putting together all sorts of offsets and circles, and these were these epicycles and deference and so on. There were ingredients that were, it's sort of strange that this wasn't noticed or complained about at the time. Like, for every planet, there was a certain offset that was always in the direction of the sun. You know, how come? Like, mathematically, it could have been in any direction. It could have been a different one for every planet. That's what we call fine-tuning in physics. When there's something in your theory that's sort of curiously aligned, like there's parameters that you all have to set to the same value, that probably means that you have too many parameters in your theory and that you could simplify it. And that's what the simplification consists of, that, you know, the going from Ptolemy to Copernicus. But I think the reason that this took so long is that Copernicus's idea, of course, unlike Kepler, was that the planets go in circles around the sun. And that's a terrible approximation. I mean, okay, you have to really look carefully to see with your eye the difference between these circles and the ellipses if I drew them on a piece of paper. But astronomical observations of the motions of the planets easily in Ptolemy's time were good enough for circles to not do the trick. They were good enough to know that circles were not the right answer. And so it was kind of a bold step for Copernicus to say, oh, you know what? I'll get it a little bit wrong, but I'll make it so much simpler. Let's see where that takes us. I mean, I don't know if that's really how he thought about it, but it feels that way from our. He must have known that he wasn't doing as well, and in fact, I think he was fiddling around with his rules to try to sort of correct for that again. So just merely putting, the sun in the center isn't all that great in terms of making your theory look simple if you insist on circles. Okay, and that's what, you know, Kepler's advance was, to realize, okay, these are actually ellipses. The sun sits in one of the focal points of the ellipse. The focal points are, for the kinds of almost circular ellipses, they're just a little bit off the center. And of course, Kepler also had laws that told you how fast the planet is moving at each point of its orbit, and it related the periodicity of the orbit to the distance. So it had these three laws. He had a fourth law, by the way. The fourth law, which we don't teach in physics classes today, was something you would do when you're on a roll, like he was. You know, he was explaining all these things so beautifully. It was all falling into place. but why do these planets have these spacings that they seem to have? Like, why is Venus this far from the sun and Mars that far and Mercury so close? And what governs these varying distances from the sun? And it seemed like a great idea to come up with a mathematical relationship for that. And he came up with an idea. It had to do with platonic solids, and you imagine like fitting them inside each other very tightly or something, and then the ratios of the distances of these different solids was supposed to correspond to the ratios of distances of different planets from the sun. And I guess there were also the right number of planets equal to the number of platonic solids or something. So it was, the details here are not important. What's important, and the reason that I bring this up, again, sort of triggered by the multiverse that Tucker reminded me of, is that today we know that this was completely wrong, right? That the distances of the planets, or the ratios of those distances, have absolutely nothing to do with any fundamental law. They're an accident, a historical accident of how our planetary system formed out of some messy gas nebulae, and there's a gazillion other solar systems out there in the world, and they're all different, and there's no law that says that these planets have to be spaced in this particular way. It's an environmental accident. There may be some way that we can understand why one of those planets is at a distance from the sun that allows for things like water to exist, right? But that, again, has nothing to do with the fundamental laws of physics. It has something to do with the fact that we're here asking the question. That doesn't make this observation unscientific. And it also doesn't mean that Kepler was stupid trying to explain the ratios of the distances of the planets. It was a noble and perfectly sensible thing to try to do, especially when he just explained so many other things. You don't know ahead of time, and this can be one of the hardest things to decide in physics, which of the phenomena we are confronted with are closely related to fundamental laws, and which are incredibly far removed from them, and are the consequence of some complicated evolution that we'll never retrace in all the details. This multiverse idea that Tucker alluded to is the idea that there might be quite a few constants, so-called constants of nature, that seem so awfully nicely tuned to allow for the complex phenomena such as ourselves to exist, that do in fact vary from place to place, and that we've just seen such a small part of the universe that we haven't seen these other regions where they take different values. And that we live in this very interesting region because, well, for the same reason that we live on a planet with water. That may be wrong, right? But there are good reasons to think that it's something we should take seriously. And just as Kepler wasn't stupid to entertain sort of first principles explanation of the planet's distances, it's not also stupid to question that. All right, good. So we've talked about gravity so far only in terms of the planets and their motions, but of course, around the time of the scientific revolution, Kepler, Copernicus, there were also the beginnings of experimentation. I mean, to the extent that I can discern science as a subject before, I don't know, 1500, 1600, I would say it was mainly astronomy. That was a systematic way of observing and trying to find patterns. What happened, let's say in 1600, when Galileo started letting balls roll down an inclined plane, was different. Not only was he observing things and writing them down in his notebook, but he was poking nature actively. He had to build that plane, he had to let the ball roll, he had to figure out ways of then measuring what happens. That was the beginning of active experimentation. It's stunning the distance between the viewpoint of the ancients, who would just declare things like, I don't know, things have a tendency to go this way or that way towards the center of the Earth, and they have they go at a fixed speed or something. I mean, they would just make stuff up, and it would not occur to them. The idea was not yet there that you could build an apparatus that would check your idea, to allow you to test this idea and tell right from wrong. Or at least, temporarily okay from wrong. Which is, that's again, I want to emphasize that everything we do is temporarily okay at best. So I think it's hard for us today to appreciate that was a thing that had to be invented, that you could just, you could try it out, check it, see if it works. So Galileo did his wonderful experiments with gravity, and it became clear that the things fall with a constant acceleration. They get faster and faster as they fall. When they seem to reach a fixed velocity, that's because of air resistance. This idea that you can separate the messy effects out from the interesting ones. You have to be able to do that. That all happened then, and I guess that was the background in which, or the setting in which Newton could come in and have this idea that there is a single law of gravity that describes the fall of objects on Earth, and also the motion of the moon and the planets and the Earth around the sun. Let's get back to this question of reality. Is this force that Newton invented real? I don't know. Maybe a show of hands. Is it real? Yes? Okay. If no, why not? Just shout.
Are boundaries conditions?
Curvature of space-time.
Good. First of all, it's wrong. The theory's wrong, right? We now know that gravity is just the curvature of space-time. It's just objects trying to go as straight as they can in a curved space-time, whatever that may mean. But I was just driving on that beautiful road from the coast, and it has these rolling hills, and you can imagine if there weren't any cows and any trees, that you could just hold your steering wheel straight and just keep going. Okay, that's what it means to move over a curved surface while going as straight as you can. It's not recommended. Sorry.
I don't quite get, is it curved space-time? Because Minkowski came up with all this math, and Einstein said, oh, it's not that. But is it the reality that gravity is the curved space-time?
Excellent question. But let's stay with the old reality first. Yeah, exactly. My point, the point that you brought out, which I think is a beautiful point, is that it was superseded, right? The idea of gravity as a force was superseded by a theory which is, under the criteria that I gave you at the very beginning, better in every respect. Just as Newton's law of gravity, of course, reproduced Kepler's ellipses, that's wonderful, and the same way that Einstein's theory reproduces Newton's theory as a limit, as an approximation, but it's better, and you can check that it's better. You can check that the planet Mercury moves in a way that is inconsistent with Newton's theory and is consistent with Einstein's theory. Okay, and so what's remarkable, right, is that these two viewpoints, a curved space-time in which things are trying to go as straight as they can, and a force, which is something we're sort of, I think we have an intuition for. We can feel a force, you can pull a spring or something, and you know what that means. That those two ways of describing something can, for all intents and purposes, be almost identical in the phenomena that they produce, is remarkable, right? And that's what should make us careful about ascribing reality to any of these things. There can be mathematical formulations that are in fact equivalent. We call these dualities in physics. You can have, two completely different looking ways of getting the exact same results in terms of what you observe, the same entries in the notebook. And, well, which of them is the reality? I don't know. So we have to be careful about being too hasty, assigning some reality to whatever theory we currently think is the best one we've got. And you know, the reason that I'm looking for quantum gravity is that I don't think Einstein's theory is the final word either. It can't be. But once we're not so sure about whether the force is real, by the way, you know, what the thing you could have said, which nobody said, but you know, it's just a construct. Have you ever seen a gravitational force? Like, is it pink? What does it look like? It's a mathematical construct, right? Does it matter? No. I mean, it got us to the moon, right? Newton's theory is good enough for that. We didn't have to go. Yeah, you gotta go with the times. Yeah. So but by the same logic, you know, the ancients didn't know what the dots were on the sky that they were observing. They didn't know what the planets were. The planets are wanderers. They're just like the things that don't look like the fixed stars. They move around. But they had no idea that they're like gas balls or rocks or ordinary things. Now we would probably say, oh, those are very real things. Right? It doesn't really matter. The point is you have a theory and describes what you see. Yeah.
Why do you think the Einstein theory is not the final theorem? Which point do you think is wrong?
Can you repeat the question?
Yeah, I'll repeat the question. The question is, why do I think that Einstein's theory is not the final word and which part is wrong? It's much more right, first of all, and that's kind of the main part of my talk. It's much more right than it has any right to be. It's amazing. But one way to quickly answer your question is that all theories which don't have quantum mechanics built into them explicitly are obviously wrong because they suffer from the same catastrophic implications that classical physics was recognized to have at the end of the 19th century and that led to the discovery of quantum mechanics. For example, this table would radiate, I mean, back then the worry was it would radiate an infinite amount of electromagnetic radiation. That's why you had to quantize the world to sort of give it fewer ways of radiating, and then it could, you know, radiate just the amount we actually see, which is a little bit of warmth depending on what temperature it is at. And if general relativity was the final word on gravity, this table would radiate an infinite amount of an infinite amount of energy per time in gravitational waves. And that's just clearly not what happens. And so, yeah, it's got to be wrong.
Electromagnetic waves?
No, gravitational waves.
Oh, pardon me.
Yeah. Yeah. The electromagnetic ones we've taken care of, right? For those, we now have a quantum mechanical theory. I think the question was, what if we left gravity alone? We're saying we're happy, Einstein was pretty smart, maybe we can just make do with this theory, it's the final word. We cannot, because the spectrum of radiation emitted by this table also includes gravitational radiation. It's imperceptibly small, but the prediction would be that it should be an infinite amount if you don't quantize gravity. Yes?
Could you maybe just give a little bit of detail about the dependency, like mass in regard to gravity, for example, something about the factors that go into describing gravity versus quantum theory? Are there differences?
Let me postpone that until, so I maybe should have said that to the last question as well. Let me postpone that until I get to the quantum part of the story, which is kind of at the end. I'll try to be at least somewhat historical in order, even though I've been jumping back and forth already quite a bit. Yeah, so we're actually almost there in a way. I do want to make a little detour because I feel like this is such a gravity-centric talk that we should perhaps just discuss briefly one other very famous story of unification in physics, which is that of electricity and magnetism. The work of Faraday and Maxwell and others, where you had these, again, naively independent phenomena of electricity, sparks flying when you hit a rock with the right way, and magnetism. Also, you have naturally magnets in nature that you can find, so probably magnetism is very old. It's been known for a long time. And through experimental study, it was understood that there's some kind of relation between these two things, that you can make an electric current flow by moving a magnet, that you can create a magnetic field by making an electric current flow. And eventually, Maxwell guessed, it's always a guess, Maxwell guessed some laws, some formulas that describe the relation between these two forces. And I want to mainly tell this story because almost every unification comes with sort of mind blown. There's always that aspect. Like, I think the ultimate one was definitely Newton. I mean, the idea that terrestrial and celestial things are the same from the point of view of like how people had lived for thousands of years and thought for thousands of years. You're not going to match that. But what happened to Maxwell was that he discovered that this is something that this electricity causing magnetism, magnetism causing electricity, is something that can just keep on going without anyone having to move anything. That once you get it going, there are these things that he called, or I think he called them, electromagnetic waves that basically have an electric and a magnetic field that are fluctuating in orthogonal directions, and that it propagates through space. Those came out of his formulas, these electromagnetic waves. He didn't start out trying to discover electromagnetic waves. It was just an inevitable consequence of the math he had just written down. But he could do more than that. He could compute the speed at which these electromagnetic waves would propagate in terms of like really weird constants that people had measured in labs related to electricity and magnetism and how they interact, like when you have solid objects in a lab, like actual magnets, and move them around. These constants, nobody cares about them now. Okay. But that's what had actually been measured. And Einstein was able to take those measured values and ask, his formulas, well, what do they imply for the speed of light? Oh. He calculated the speed at which his electromagnetic waves move, and he found that it matches the known speed of light. The speed of light had been measured by that time. It's not so insanely hard to measure it. But he didn't know that going in. He just wanted to study electricity and magnetism. He wanted to put them together. He succeeded with that. And a minute later he discovers, oh, light is nothing but electricity and magnetism. That wasn't known before. That wasn't obvious at all. Who knew? It's an electromagnetic wave. So this is like, wow, you want to have that's what we live for. It's a moment like that. Like to think, him sitting there, like being the only person in the world who knows that right now. Like just take it all in, It's insane. Good, but back to the program, since we don't have forever. So yeah, let's get back to quantum mechanics. Now I can say get back because you guys made me already talk about it quite a bit. Quantum mechanics, I would say, is a theory that we were really dragged to kicking and screaming. We were dragged to by an abundance of observations, but also by the existence of certain, what you might call paradoxes or catastrophes, like what I just mentioned. It became, in the 19th century, with the Industrial Revolution and so on, it was very important to understand thermodynamics, to understand how engines work, what heat is and work, and how they relate to each other. And this was an extremely highly studied subject, and lots of things were discovered about it. And one of the things that were discovered is that basically whatever can wiggle about a system will wiggle, at a strength that's related to its temperature. So for example, all the atoms in this table, they're sort of wiggling around a little bit because the table is not at exactly zero, absolute zero temperature. And as a result, it actually emits infrared light. The sun, of course, emits visible light. It wiggles much more strongly. And you can calculate how much power in this electromagnetic radiation, be it infrared or visible or anything else, is emitted by the table. And what you find is that to a physicist, an atom wiggling at this speed, that's one way it can wiggle. But an atom wiggling at that speed, that's a completely different way it can wiggle. Okay? And it'll do both. Now, it'll sort of not, the amplitude with which it'll wiggle faster will be smaller because, you know, we're giving it the same amount of energy for every way it can wiggle. That's sort of the basic rule. But there's no limit to how fast it could wiggle. And for each of those ways, double it again, it will emit a certain amount of energy. And when you add up all this energy it emits, it's infinity. That is the so-called ultraviolet catastrophe. Why ultraviolet? Because ultraviolet light is at the fast wiggling end of the spectrum that we can see, and physicists like to use it as a shorthand for wiggle fast. Okay, and so the fast wiggling adds up to an infinite amount of energy emitted, and that's obviously nonsense. The converse of this would be that it would take an infinite amount of energy to heat this table up to the temperature it currently has. So nothing would, I mean, everything would be frozen. If this was right, it just doesn't make any sense. And I think this is a nice example of how you don't always need incredibly precise observations to know that your theory is wrong. Very often, there's something about it which is just completely nonsensical, even though it gives you like incredibly great results for almost all purposes that you've ever used it for. I mean, the steam engine did work, right? But there was something about the theory that was just catastrophically wrong. Now, I don't think that was enough. It was actually enough for the first step to quantum mechanics. The first step was Planck in 1900. Max Planck, he came up with this sort of completely ad hoc rule that there's only certain kinds of wigglings that are allowed. Okay, and that there are certain discrete amounts of energy that must be emitted, and in that case, the really fast wigglers, they don't get there. They don't have the ability to emit in that way, and that kind of cuts off the spectrum, and more importantly, cuts off the infinity and leaves you with a finite amount of emitted radiation. He kind of just made that up. And it was, it was already, he already had more data than just knowing that things don't emit an infinite amount of heat. People had actually measured the spectrum. And spectrum means, like if I have a hot body, you can measure how much red it emits and how much energy in blue it emits and so on. You can look at all these different wavelengths, and it forms a nice little curve where you can sort of try and come up with a formula that matches that curve, and that's what he did. And he was actually a very conservative guy. Plus, I think he was already 40 years old or something, which is absolutely ancient for a physicist. I'm not totally sure, but I think it's true. And so he hated the idea. As far as I know, he was not a fan of himself at all. But it was a desperate move, and that's usually this is the difference between a great physicist and a crackpot, right? The crackpot will just jump at some random crazy thing with absolutely no hope of even connecting it back to anything that was ever known before. And the great physicist will resist change until they're absolutely why? Because otherwise it's random, right? The reason that he eventually took the right step is that he wasn't hasty, jumping to all sorts of conclusions, or not caring about the data that were around, that you, after all, have to keep it happy, right? You have to make sure you don't invent something that's totally in conflict with what's been observed. A couple of years later, as part of his famous, very productive 1905 year, Einstein had the idea of saying, well, if this is how bodies emit radiation, this is probably also how bodies absorb radiation in chunks, in quanta, not arbitrary amounts, but only certain quantized amounts are allowed. And he was able to explain something called the photoelectric effect. Using this assumption, it's not something we'll have time to discuss in detail, but those were sort of the first baby steps. Emission of radiation is quantized, absorption of radiation is quantized. Of course, Einstein figured, well, in that case, probably the things that are traveling, from the emission from the table until the photon hits me are quantized particles. I just said the name we give to this today, photon. But what we really needed to complete the theory was something much more radical than those simple words of saying, okay, things can only come in certain units. I mean, it's something that's actually fairly intuitive. Like, I don't know, it's like you can only be pregnant with 1 or 2 or 3 kids. It comes in units, or you can only order this many boxes of cereal. But something insidious and much more confusing happened at the same time. People were studying atomic spectra. They were studying how elementary particles move and interact. And explaining all those things forced them to a theory which was completely different from classical mechanics. It wasn't just adding this one extra condition. Oh, you gotta emit particles, energy, whatever, in these certain quanta. I give you a formula for how big the cereal boxes are allowed to be, and now we're done. Everything else is the same. No, everything was completely different. And how was it different? Well, in classical mechanics and in our brains, let's be honest, there is no difference between the state of the system and what I can observe about it, states and observables. What I mean by that is, if I have a cannonball and it's flying, what can I observe about it? I can observe where it is and how fast it's moving and in which direction, right? Position and velocity. Probably other things too, maybe it's spinning and so on. Let's keep it simple, right? I can also tell you the state of the cannonball. Well, how? I would tell you its position and its velocity. The exact same things that I can observe about it. It's like, duh, of course. Like, that, if that's what you can observe about it, that's how you would describe the state, by giving the other person those numbers. And now they know what the cannonball is doing and where it is. Right? It seems like the most obvious thing in the world that those two things are the same. But in fact, they are not. And it's tempting to say in quantum mechanics they are not, but that's the world. In the real world, they are not the same. They're different. So there is one mathematical object that we use to describe the state of the system. And there's another mathematical object that we use to describe what you can measure about it. And you cannot describe the state of the system by telling another person all the things that you could measure about it. Those are just different things. And if you know the state of the system, that doesn't necessarily know what you get when you measure certain quantities about it. If I know a particle is in this particular place, for example, then famously, I cannot predict what I'll get if I measure its velocity. Conversely, if I know how fast it's moving, I can't predict where I'm going to find it exactly. Okay. I can tell you even a little bit more, which I think is still intuitive, even if it's hopefully mind-blowing. If it's not, then I'm not doing my job. The state of a system is a vector in a certain space of vectors. Vectors aren't that hard to understand. Like, you can draw them on a piece of paper like it's an arrow. Let's call this the origin of this piece of paper, and a vector might go here. Okay, so that vector goes, 4 inches in the x direction and 2 inches in the y direction. That's a vector. And I can add to it another vector that maybe goes this way. I can sum them up and I get a third vector. That's their sum. It's just literally like a child's game. You can do it at home. Vector addition works in any number of dimensions, of course. It works also in 3 dimensions and 100 dimensions mathematically. It doesn't matter. Well, the state of the system is a vector. And that means that you get to add states of a system. For example, this table standing here with all of you being where you are, that is a state of the system we call this room. This table standing over here instead, hypothetically, is clearly also a state. I mean, if I did the work, I could move it there. You'll hopefully believe me that this is a valid physical state that we could accomplish. But because each of these states is a vector, that means that I get to add them together. There is such a thing as table here plus there. That's not 2 tables. It is the state where the table is here plus the state where the table is there. Just like you can add 2 vectors. You may have heard this in the context of a cat that's alive plus dead. It's called Schrödinger's cat. But why do we think this is right? Well, you might ask, why have we never seen a cat that's alive plus dead, or a table that's like somehow both here and there? Actually, this is one of the embarrassments of my field, that it took people about 50 years to understand that. Normally, I've emphasized this a few times before, when you come up with a new theory, the first thing you check is that you can recover the old theory, at least in the regime where it was working. Einstein going back to Newton going back to Kepler. You can do the work. It's sometimes really surprising how the old thing comes out of the new one in the limit where the old thing was working well, but it's got to do that. With quantum mechanics, it took people forever to understand how classical mechanics emerges from it. And I think it's because of a fascinating novelty that physicists are trained to ignore. Things like air molecules and light molecules bouncing off this table, or off a cannonball that's flying, right? We were talking about earlier the air resistance messing up, the nice laws of acceleration of a falling object and so on. We're trained to ignore that kind of stuff so that we can discern the real, important, clean laws and learn how to ignore the messy bits. But it turns out that a state in which the table is here plus there would not survive unless we remove all the air molecules from this room, we turn off all the lights, and we also cool the room to 0 temperature, including the tables, very importantly. There are interactions that would otherwise immediately what is called decohere this state. A different way of saying that is that you cannot neglect an environment that seems to a classical physicist completely negligible. This table is not, in fact, evolving by itself. It's not an isolated system, and that turns out to be incredibly important. It's constantly interacting with light particles and molecules of the air and so on. And you have to get rid of all of these to prepare a state and keep it there in which the table is here plus there. But the reason that I'm confident that this is only a practical problem and not somehow a sign that we've lost our minds thinking that such a thing exists, is that with elementary particles, we can prepare such states with no problem at all. It's not hard to shield them from the rest of the world. In fact, you can have an electron. Electrons have something called a spin. It's not exactly like a spinning top, but think of it that way for the purposes of this discussion. And this spin can point in any direction, this way, that way. Okay. But somehow, this vector space that describes the states of an electron spin is actually a 2-dimensional vector space. Why do it's like this? It's like this sheet of paper. There's only 2 ways you can go: right and left, and up and down. Okay. So, in which sense is that true? Well, there's vectors which are what are called orthogonal. That's, we would say, about as different as they can be from each other. There are vectors that are parallel. For the purposes of quantum mechanics, they're actually the same. It doesn't even matter how long they are. And then there's like vectors which are kind of in between. Okay. Those are, in some sense, different states that a system can have, but they're not maximally different like the orthogonal vectors. Now, the orthogonal vectors in this way that an electron can spin, an example of two orthogonal vectors, I mean, there's many examples, right? These two are orthogonal, these two are orthogonal. An example of them is the spin points up, and another example, and the sort of maximally different way it can spin is the spin points down. Spinning top is the other way around. I can add those two maximally different states, like adding these kinds of vectors. I'll get a vector that looks like this, right? If I add them, I get a vector that looks sideways at 45 degrees. That's, again, a state that I can just directly identify physically as an electron that's spinning sideways. And if I measure which way the electron is spinning, if it's in that state, I will definitely find that, yes, it's spinning sideways. So this absurd sounding idea that different states of a system can be added to one another becomes an everyday reality in the world of small particles, where we can successfully eliminate interactions with the rest of the world and keep them in a sort of nice, pristine environment where we can manipulate them in that way. One of the mistakes, I think, of the early decades of quantum mechanics was the idea, which at least I interpret Bohr to have propagated, for example, that there's some sort of fundamental distinction between the microscopic world and the macroscopic world, and that is what explains why we never see cats that are alive plus dead, or tables here plus there. That there's kind of a boundary you have to draw, a line between things so small enough to be governed by quantum mechanics and things where quantum mechanics is just somehow no longer valid. That is a terrible thing to say. It is completely counter to the spirit of unification that has, that underlies the entire history of physics. If quantum mechanics is valid for small things, it must be valid for big things. It's just that it's hard to see certain quantum mechanical phenomena, those for which it's important to keep disturbances away. Big things tend to get disturbed very quickly. Yeah.
So you were talking about the Heisenberg uncertainty, just like
Yeah.
right? And so we want to observe something, but according to Heisenberg uncertainty, it's not quite possible, because when we observe something, we need to put light on it, and its photons now this will disturb whatever we want to observe.
Yeah.
But if you want to observe, that requires light. If we want to eliminate everything, like in an electron, how can we still observe something without disturbing?
Yeah. So,
The question again?
yeah, let me repeat the question. So, the way that so I never actually, I think I didn't say the word uncertainty principle, so let me back up and say that when I told you that if you know where a particle is, then, and then you measure its velocity, I can't predict for you what you're going to find. That is a consequence of what was called the uncertainty principle by Heisenberg. In physics, at least half of things that are called principle are not. It's not the most fundamental way to think about the issue. The fundamental way to think about the issue is the one that I presented to you when I said that quantum mechanics is different from classical mechanics because states and observables are mathematically different objects. And to know the state of a system can be in a very definite state, but you're still not necessarily going to know what you're going to find when you observe something. Now, when you say, good. So this Heisenberg uncertainty principle was often how people were trying to process the novelty of quantum mechanics. Like, how can it be that I can't know simultaneously where something is and how fast it's moving? I mean, if that was really true, you could get out of every traffic ticket, and it'd be amazing. So what you do is you concoct these thought experiments. Like, what if I actually, so I know this electron is moving at this or that speed, and now I try to find out where it is, or I build some slits that it has to go through, and I follow these thought experiments, and I see that there's some kind of conspiracy that seems to be preventing me from succeeding in measuring both things simultaneously, right? And there's nothing wrong with that analysis. But I would say it's a step removed from the real insight. The real insight is what I said. It's a very general principle. It's not a conspiracy. It's similar to, whenever we have a radical new theories are usually radical seeming, like Einstein with the special relativity, let's say. And then, you have these weird phenomena that things seem to contract in length when they move fast, and clocks run slower, and so on. And you start concocting thought experiments, like, this violates our intuition so greatly, and how can it possibly make any sense? And you come up with experiments that seem to lead to necessarily to the conclusion that the theory is just inconsistent, and it gives you logically inconsistent statements, and somehow it always wiggles out, right? And that's great. It's like, it's like the 5 stages of grief or something. It's the denial stage. You got to work yourself through it. But in the end, when you're done with it, and when you've done enough of these exercises to realize you're up against something that is much more powerful than you, and that actually hangs together and works, then you want to go back and look at the theory from the simplest possible viewpoint. In Einstein's case, special relativity, it's a statement about the structure of space and time being just fundamentally different from Newtonian space-time. The set of points that are simultaneously with this event is not 3-dimensional but 4-dimensional. It's a completely different structure. And you want to try to absorb that and get a little bit closer to it becoming an intuition, even though we're not, we don't grow up in that world, our brains aren't wired for it. But ultimately, you want to take the real lesson away and get over the fact that it's not like things are not as they seem. To me, that was the most exciting thing that got me into physics, that things are not as they seem, but they're also not random. As I said, you get dragged kicking and screaming sometimes. The most absurd, crazy sounding claims about how nature works that, are correct and are inevitable and are so crazy that nobody would have dreamed them up in their armchair. They're much crazier than that. When I get crackpot emails, and I get a couple every day, the thing that's most disappointing about them is how unimaginative they are. It's terrible. All right, so initially quantum mechanics was mostly used for things like atoms, elementary particles, individual particles, and how they behave, and so on. But in the course of the next 50 years, let's say 1925 to 75, people figured out how to describe what are called quantum fields. Okay, what do I mean by that? Well, one way of motivating that is to say, well, we already knew that, for example, electricity and magnetism, they were described in terms of something called a field, meaning, for example, I tell you at every point in space in which way the electric field is pointing and what its strength is. That's what we would call a field. Same thing for the magnetic field, and then you have laws that describe how these propagate. Well, none of those laws, the laws found by Maxwell, were quantum. None of those incorporated the important message that you better have cereal box sized portions of energy that can be emitted and absorbed and so on, and so they needed quantizing. Right? You can't always just talk about one atom and one electron. So you want to start getting back to the physics you were doing before, like electromagnetism, some 19th century story. And you've got to make it consistent with this idea that things come in chunks, or else your table will go back to radiating an infinite amount of energy in finite time, and that would be bad. And people discovered how to sort of do that. It almost became like turning a crank. You quantize the field. Okay? You take the classical one, you quantize it. There's certain rules for how to do that. It's not critical here that we go in detail through those rules, but there's something called quantum electrodynamics that accomplished this task. And it, as usual, you can get Maxwell's theory coming out of that in certain limits, in certain regimes where things are supposed to behave classically. We can't tell the difference, but it describes all those fields in a way that's consistent with the basic quantum principle of not everything goes, things come in chunks. There were even new forces that were discovered in subatomic physics called the strong and weak nuclear force through the study of radioactivity originally. And those forces are very important. Without those forces, we wouldn't understand what holds the nuclei of an atom together. The nucleus of an atom consists of positively charged and neutral particles. And so why don't they just fly apart? Positive charges repel. And well, that's because there's a much stronger force at play that holds them together, at least until you try to make atoms whose nuclei are too big. At some point, this doesn't work anymore, and that's why we only have so many elements, and not far more. Those two can be described in this language of quantum field theory. In fact, they were actually only discovered in that form from the start, because they were only discovered after we already had quantum mechanics. There's no classical version of them, basically. So that's great, and that's, I think, where things stood at about 1975. And you will have noticed that the thing we didn't quantize yet, the thing to which we didn't feed into our machine and turn the crank and make it more quantum, was gravity. Okay. And around this time, actually, people tried to do this. I mean, we have this great machine, we know how to turn the crank, let's feed gravity in, and the machine blew up in their faces and exploded, and nonsense came out and nothing but infinities. And that was weird. That was a new experience that it's hard to overstate how successful this program of quantum field theory was. People were building all these accelerators in the 50s, 60s, 70s, 80s, and they were producing all these elementary particles nobody had ever heard of, and then people were using these theories to predict which one should be discovered next, and there they were with exactly whatever the mass and the charge and whatever properties you wanted them to have, and people were feeling really good about themselves, right? And then you try gravity and the whole thing is just completely useless. Well, perhaps accidentally, perhaps not, I will never know. Around the same time, there was a very important development in the study of gravity that perhaps, in hindsight certainly, explains why the machine blew up and why we were doing real violence to the whole problem of unifying quantum mechanics and gravity by trying to feed gravity into this machine and turn the crank and treat it like other forces. Hint, first of all, we've already learned that gravity is not a force. Right? I've mentioned this a few times. In 1915, Einstein taught us that what we call the effects of gravity can be better described by things moving as straight as possible in a curved space-time geometry. So it's not a force, for one. Okay, that's closely related. But something much more dramatic and concrete happened in the early 70s, starting with the work of Jacob Bekenstein in 1972, and the discovery by Hawking of the fact that black holes emit radiation in 1974. So why are these things so remarkable? So we'll have to do a little bit of thermodynamics just now. Okay. We've been talking about it for a while, the table emitting heat and so on. We can ask, how much energy and heat does this table emit if I let it cool from, I don't know, 68 Fahrenheit to 67 Fahrenheit? That's a concrete question, and we can do that experiment in a lab. We can let it cool off by 1 degree Fahrenheit, and we can capture all the heat that comes out of it, and we can, in a calorimeter or something, and we'll know how much energy it came out of it for that tiny little difference in temperature. Okay. That relation between how much energy comes out of it for a tiny little difference in temperature, that's something that people were already obsessing over in the 19th century, and they called this entropy. It's the entropy of the table that's basically the proportionality constant between how much energy is emitted per degree Fahrenheit that it cools off. Why is this an interesting quantity? In the 19th century, it was mostly a convenient quantity, a bit like the gravitational force, this very abstract thing that isn't pink and you can't touch it, and it's just a mathematical quantity that's very useful for designing heat engines and making sure they work and don't blow up and so on. But today, we understand that the entropy has something to do with how many ways the table can wiggle. If the table consisted of molecules that have more degrees of freedom, they can maybe wiggle by rotating in addition to just like up and down and left and right and so on, then it would emit more energy when it cools off by 1 degree, because it's still true in quantum mechanics, as in the old days, that if a thing is at a certain temperature, it'll use all its ways of wiggling, and with a strength that's sort of set by the temperature. It'll distribute, every way of wiggling has a certain energy to it that is set by the temperature. And so, in hindsight, 20th century perspective, by measuring how much energy came out of this table when it cooled off by 1 degree, we will have learned something about its microscopic structure. Even if I don't know what this table is made of, I might be able to tell you, oh yeah, okay, that amount of energy per temperature, that must have been an iron table, or it must have been a wood table. Because all these materials, they can wiggle only in certain ways that are characteristic for them. That depends on how they're made, put together, but it depends on the microscopic constituents, the atoms, the molecules. So this boring 19th century quantity is actually something that lets us look inside things. It lets us look at the microscopic structure. And that's why people were able to measure something called the entropy, which today I intuitively think of, well, yeah, how many ways can something wiggle? I immediately think of it in terms of like the microscopic structure. I think of the atoms doing their wiggling. People didn't know what atoms were in the 19th century, but they knew how to measure this thing. All right. Well, why am I telling you this story? Because the consequence of Bekenstein's and Hawking's work was that we knew what the entropy of a black hole is. How do we know that? Well, for example, Bekenstein just kind of guessed it, long story. And Hawking thought it was preposterous, because if black holes had an entropy, then they would, by something called the first law of thermodynamics, they would also have a temperature. And that's ridiculous, then they'd have to radiate. He literally said that in like 1972. And then 2 years later, he does a completely unrelated calculation, discovers that black holes actually do radiate, with exactly the temperature that is necessary for Bekenstein's guess to have been right. Okay, so then it all fell into place, and it hung together and so on. But we were stuck with this idea that black holes have an entropy. In other words, they have a certain calculable number of ways of wiggling. It's like you know what the atoms in the table are. But nobody had ever measured a black hole lose some temperature in a lab and measured how much energy came out or something like that. Nor did either Bekenstein or Hawking have the slightest clue or make any assumptions about what the atoms of a black hole are. No clue. And yet, somehow, by just doing some calculation that basically involves gravity and a very naive little bit of amount of quantum mechanics, basically using the kind of quantum field theories people had already worked out, they were able to find out how many quantum states a black hole has, in how many different ways is it allowed to wiggle. I forgot to explain what a black hole is, because I think by now you guys all know that. But it's something that, it's a very fundamental object in Einstein's theory, something that we now know really exists in the universe with very high probability, where an object just gravitationally collapses completely. And it forms what's called an event horizon, which if you cross, you're not going to come back out. And so classically, it's a completely black thing. That's why, hence the name, right? If you go in, you can't come out. In particular, light can't come out. But what Hawking found is that quantum mechanically, those objects radiate. And as a consequence, we now knew how many states they have. This was not how people thought about it at the time, but that was the actual scandal. The scandal about Hawking's discovery was that you are not supposed to be able to know how many quantum states an object has, of which you know neither the microscopic structure nor are you able to experiment with it. That was outrageous. For some reason, people all focused on the fact that black holes radiate when they weren't supposed to radiate. That seems like a minor issue. As we discussed earlier, radiation of ordinary objects also doesn't make any sense when you don't treat them quantum mechanically. Black holes had not been treated at all quantum mechanically until Hawking, so maybe it wasn't so surprising that they looked like they weren't radiating. What this meant was that effectively classical gravity knows about its own quantum states. This theory that Einstein wrote down, which is, well, okay, it has curved space-time, but it's not crazy like quantum mechanics where you can add like table here plus there. There's different levels of crazy. And believe me, curved space-time is like harmless compared to that. That boring, old school theory seemed to know something about quantum mechanics. It was already inside. It took a while for this to become, for us to recognize, I think, that this was the right way of thinking about that discovery. So 25 years later, I discovered, and building on work by Lenny Susskind and et Hooft and others, I discovered that gravity not only knows about its own quantum states, those of black holes, which are intrinsically gravitational objects, it also knows about the quantum states of matter, of everybody, you, me, everything. This is really remarkable. Let me give you a quick sketch of why that has to work. So the reason that that Bekenstein in '72 came up with the guess that black holes have to have a certain entropy, a very specific guess. The entropy should be proportional to the area of the surface of no return, the event horizon. He came up with that guess because of a little thing called the second law of thermodynamics, which you definitely don't want to mess with. The second law of thermodynamics says that sort of ordinary evolution, unless you intervene from the outside, the entropy of systems will be overwhelmingly likely to increase, extremely unlikely to decrease. For example, the air in this room is extremely unlikely to collect in the corner over there, even though that's clearly an allowed state for it to be in. It's just that there are very few ways that very few different states it can be in microscopically if it's all in the corner of the room. And there are far more states it can be in microscopically if it's distributed evenly throughout the room. And that's so overwhelmingly more likely. There's so overwhelmingly more that we never see such a crazy thing. But it's just a statistical statement. Anyway, Bekenstein realized that you could destroy entropy by throwing stuff into a black hole. This sounds like a weird thing to worry about. I mean, I could take the air in this room and throw it into a black hole, or usually people like to throw a hot cup of tea into the black hole, and then it's gone. And you might say, okay, well, why don't you jump in after the hot cup of tea? And I mean, if it's your personal problem that you don't want to go into a black hole, but there it is, right? It's not like the entropy suddenly disappears. Well, actually, it's not so simple. If you wait for a little while after you throw the hot cup of tea in, the way that the causal structure of space-time works in Einstein's theory is such that you cannot catch up with the thing. So for all practical purposes, that tea is gone. And so is its entropy. And this would still not have bothered a lesser mind than Bekenstein. I mean, it's just like, okay, tough luck, you can't get to it now. But but to him it was like, no, this is the end of the world, because the second law of thermodynamics means nothing if I can't check that it's true. And once there are black holes around, evidently it loses all meaning. It loses all of its power. I can just disappear entropy into a black hole. And so he came up with the idea that this has to work like when I put the hot cup of tea in the fridge. The tea gets colder, which means that its entropy goes down, but the fridge heats up the room. Something else compensates. That's always how it works. You can always decrease the entropy of some system by brute force, if you will, but there'll be some overall increase in the world as a result. And so his idea was that the area of the black hole horizon will increase by enough to make up for this lost entropy, which is something that makes sense once you've declared that the area of the black hole horizon is the entropy of the black hole. That area growing is the equivalent of the fridge heating up the room and more than compensating for the lost entropy of what went into the fridge. Okay. But now you maybe can start seeing why gravity has to know something about the quantum states of matter for this to work. And then we get back to conspiracy theories. It sounds like a crazy idea. You start, how does the black hole, which responds to simple things like how much mass you threw in, and now it's gotten bigger. And that's what a black hole cares about. It can't possibly know whether the tea was this or that hot, or whether it was water or mercury or alcohol that was in that cup or something, right? How can it possibly know that? It only cares about the mass of what you threw in. And that's what determines how much bigger it is. And yet when you play with it and you do the calculation, you find out that it always works. And eventually you come around and you say, okay, fine, I give up. I believe you, Bekenstein. I believe what you called the generalized second law of thermodynamics, which is really just the second law with black holes included. Okay. But the miracle remains that somehow space-time and the way it responds to matter knows something about the quantum states of matter. How many ways something can wiggle microscopically. And this is what I leveraged in 1999 in inventing something called the covariant entropy bound, and claiming that very generally the surfaces of arbitrary surfaces anywhere in the universe give you an upper bound on the amount of entropy of matter, the number of ways things can wiggle in a certain region in their vicinity called a light sheet. There's some ways to construct that it's very precise. I won't go into the details, but my point is gravity knows about its own quantum states. Gravity knows about the quantum states of matter. I don't mean to say that we already have a quantum theory of gravity in Einstein's General Relativity. It doesn't know how to prevent the table from radiating an infinite amount of energy in gravitational waves. It just isn't the quantumness of it isn't manifest yet. It's more like something else. It's more like an oracle. It's that if you ask it the right question and you ask it nicely in just the right way, gravity will tell you stuff. And the reason that I'm really confident that this is the right way to think about it, for me the real sea change was, again, several years later in 2015, when a number of collaborators of mine and students of mine and my collaborator Aaron Wall, for the first time used gravity as a discovery tool. We used this weird oracle to discover something new about this old subject of quantum field theory, which is supposedly completely well understood. Well, nobody had ever found a lower bound on the energy density of matter, meaning how much energy or mass can you have in a tiny little volume of space. In quantum field theory, that actually can be negative. And so there was no lower bound known. So we asked gravity nicely, gravity, please tell us, could there be a lower bound in this? And gravity told us. And it said, yes, there's a lower bound, and it depends on the information flow, the flow of quantum information across this point, which isn't intuitively immediately related to how much energy there is, or how negative the energy can be, or something like that. But that's what gravity said. You know, the steam came out of the hole in the ground, and the oracle spoke, and we said, okay, but we can check the oracle, because quantum field theory is, while it's a well-studied subject, and it would be kind of embarrassing if such a simple relation as what you, oracle, claim was true, and nobody discovered it for like nearly 100 years. I mean, that's pathetic. But let's check. We can check. It's, you know, we can do the calculation. Well, it took a little longer. The calculation is really hard. It's like 100 pages. We actually only did a simple case, and we left the hard work for another group. We only like checked in the case where particles don't even interact with each other, which is like really dumb. And even that was like 25 pages. But anyway, at the end of the day, it turns out it's true. It's right. And you need like everything in the kitchen sink in terms of technology developed in quantum field theory to prove that. We got it like not literally by asking a scheming oracle, but it was 2 lines of algebra from a guess about how quantum gravity should work. So that to me was like, that changed everything. Like, gravity is a monster. It can tell us completely new things that had not been discovered before. We can check that they're true because they are about a subject which doesn't even involve gravity. Just ordinary quantum field theory, ordinary matter interacting in ways with like gravity being completely like the stuff we already thought we're done with that. We're finished. We completely understand it. It can teach us new things about that. And not surprisingly, maybe this led to, you know, a really dramatic exponential growth in results and in progress. And the oracle became a kind of chatterbox. We saw that, for example, when in 2019, so by now I guess 6 years ago, my colleague and collaborator Jeff Pennington was able to ask gravity a question, a very famous question: does information come back out of black holes when they emit this Hawking radiation? Will the Hawking radiation be different if I made the black hole out of this or that kind of star, or if I made the black hole out of a herd of camels that I collapsed, or will it betray what went in? That's normally how quantum mechanics works. If you look at the state at a later time, you can figure out what it was at an earlier time. There was a famous long debate started by Hawking, claiming that the information is truly, truly lost, not just practically, but really gone. And there were a number of reasons why we had come to think that it's probably not lost, despite the fact that Hawking didn't make any obvious mistake in his calculation. But none of those reasons were, how would you say, entirely pure. They all involved extraneous assumptions, maybe something about how quantum gravity should work, that you know, you have to assume that string theory is right, which, you know, could be. These were not crazy assumptions. They gave us lots of good results in other contexts, and the evidence accumulated that black holes probably do return the information. But Jeff just asked the oracle. He just used gravity to do the calculation. No other things, no string theory, no, you know, hypotheses of any other kind. And the oracle said, yes, it comes back out. And there's a specific curve that describes the rate at which it comes back out, called the Page curve. And he was able to derive that, and there was a competing group that did the same thing at the same time. That's another great example of the oracle at work. Another colleague of mine at Berkeley, Luca Iesu, was able to compute the exact integer number of quantum states that a black hole can have. Normally, the entropy, roughly speaking, the exponential of the entropy. So, you know, if entropy is like 100, take 2 times 2 times 2 times 2 100 times, except it's not 2, but some other number. That's how many quantum states the object can have. But that's usually just an approximation. There are corrections to that at some finite temperature. This will never be exactly an integer. It's really a probability distribution where some states are more likely than others, and you use that weighted average to get a number. But there are some cases where black holes have an exponentially large but integer, exact, countable, sharp integer number of states. They're called supersymmetric black holes at zero temperature. And it was like the great triumph of string theory in the mid-1990s, being for the first time able to compute that number. And that was another kitchen sink moment. You had to use all the technology from string theory. You may have heard of deep-range dualities, this, that, and the other thing. And it involved various conjectures that we still don't know if they're really correct, but at least, we got that number out. And the computation was such that it could only be an integer from the start. It was obvious you were going to get an integer. That was not surprising. But you got something that also looked like it was e to the area, so that was nice. The way that Luca did the calculation is completely different. He asked the oracle. The oracle tells you, well, take all the ways that you can, make space-time geometries that have the same, subject to a certain set of rules that are related to the black hole that you're interested in, counting the number of states of. And then, each of these ways gives you a number, and that number is not at all an integer. It's it's not even a real number, it's a complex number. And you add up these infinitely many non-integer numbers, and obviously that's not going to give you an integer, right? Except, about 100 years ago, some mathematicians, Hardy, Ramanujan, and others, they were interested in a problem that was about integers. They were interested in the partitions of an integer. Like, how many ways can you write, 4 as a sum of integers? Well, 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 3, and so on. Right? So there's a number, you write them all down. It's a fairly small number for 4, but it's like insanely large if you want to write down the number of partitions of 100. Okay. So it becomes convenient to have approximation formulas in which, you have a quick formula you work out, and it doesn't give you exactly an integer, but if it's good enough, you can just round it and you get the answer. And they came up with ideas like that. And later, a guy called Rademacher, also a mathematician. This is like pure number theory. It's like got nothing to do with the real world, seemingly. Was able to improve this Hardy-Ramanujan formula into an infinite set of terms that you could, in principle, all work out, and prove that they give you the exact integer that is the answer to the partition problem. What Luca found when he was asking the oracle is that the oracle was spitting out that exact sequence of terms, none of which was an integer, but it was precisely the Hardy-Ramanujan sum, of which because people worked it out 100 years ago, that it sums exactly to an integer, and you know which one. And so it's also very nice to see number theory finally making an important appearance in theoretical physics. But what a story, right? I mean, this was something that, having been involved in this development, and definitely a champion of the idea of trusting gravity with teaching us about quantum mechanics, about quantum gravity, and so on, I would have said this is absolutely not going to happen. I would have never thought that you could do something that's sort of infinitely precise involving exponentially large numbers. It totally blew my mind. So, upshot, we're still not there. We still don't have a quantum theory of gravity. But we've opened a whole new direction of how to go about it, which is, in some ways, I would say a direction that goes back to maybe a traditional way of doing physics, where you try to discern patterns in the phenomena that you've already discovered. Einstein's theory of gravity that's giving us all these interesting results is a theory we've already very well tested. We know it's quite accurate. It describes cosmology and the solar system and the apple and everything you want. Rather than, for example, saying, I think string theory is a very interesting approach, but there you're basically being asked to say, well, let's go with this. We have no evidence so far that it's the correct theory. It just seems really rich, really rigid, and we can explore it and hope for the best that we will one day make contact with the real world. And we may still. But this is a different direction. This is one where we're looking at the theories we've got. We're trying to discern what's funny about them, what's weird about them, what are they trying to tell us about what's next. And I think the fact that a classical theory like gravity knows so much about quantum mechanics is telling us that it doesn't need to be quantized in the old-fashioned sense of turning that crank. It's a different problem. It's not like anything we've seen before. And I'm sure our mind will be blown when we finally figure it out. So thank you.
Please, I imagine that Professor Bousso will enjoy some questions. Do you have any you would like to throw this way?
Yes, I do have a question. So you mentioned entropy being in black holes and how entropy itself kind of measure in the sense of whatever, I'm assuming the Schwarzschild radius, which is similar to what you were describing. Is that also true for things like white holes? Like, do you see white holes as being having a similar sort of quantum? Is there a way to describe white holes or the similar approach?
Yeah, so the question was whether we should assign an entropy to white holes as well as black holes. And of course, that will require me to explain what a white hole is. A white hole is the time reverse of a black hole. So, and this is, we don't think there are any, right? And the reason that we don't think there are any is that classically nothing can come out of a black hole. So a black hole is something where, a star collapses, and in the end you have this object, and before Hawking's discovery we would have said, that's it. It can't, the reverse will never happen. Hawking's discovery is effectively the statement that all black holes are also white holes. The black hole is radiating, right? There is a process by which the black hole converts itself back to ordinary matter. Now, it is far more likely that the black hole emits this fairly boring-looking Hawking radiation than that it simply converts itself back, for example, into the star that originally formed it. But that's the question of probabilities. The in-principle question of, like, are black holes and white holes really different is answered in the negative by the fact that black holes evaporate. So this was a distinction that made sense so long as black holes behaved completely classically and nothing could come out of them. Then it made sense to distinguish between objects that first are matter and then a black hole, and objects that are first like a black hole and then are matter. But now it no longer makes sense to distinguish between them, and all the things I said should apply to this one thing that, to this exchange between matter and geometry. Yeah.
I would ask about what made people think that the gravity is the oracle, and also like how do you use the gravity? Do you mean by gravity? Do you mean like gravitational wave that's using?
Do I mean? Sorry, what was the last thing?
Gravitational wave.
Ah, good. Yeah. So you're asking about the history, and of how we came to think of gravity as an oracle, as gravity knowing something about quantum mechanics. And the history is always messy, and I'm sure that different people will give you a different, for me, I would say it was a career-defining thing. I mean, I started out by working on this problem of how gravity constrains the quantum states of matter, and there were a large, this was quite a big discussion at the time, and there was a huge amount of skepticism that this could work. A lot of people had written papers that tried to sort of establish such a relation, and they all were shown to be false. They were all like saying, oh, the areas of surfaces related to this or that, and you could just find a counterexample that obviously tells you this is not true. And so after like 15 papers like this, I think the general mood was that this probably just doesn't work. So it was not at all obvious, I can attest, in 1999 when I just came out of grad school, that gravity had this sort of power. And I think by solving that problem, I obviously got very excited about the fact that it worked. Like, that was sort of, for me, this was the big aha moment. I wrote down this relation after trying like a million other things. And then came the question of like, will it survive any more tests than all my previous failed attempts and those of many other people. And then you start seeing, oh my God, something is really clicking here. Something's really working. It's like holding together, and it's this conspiratorial stuff starts happening, right? And after a while, you think like, okay, probably like let's just say that this works. And so that for me was the moment when I think it became clear that gravity is much more powerful than it had any right to be. But it was still, at that point it was just a miracle of some sort. It wasn't yet teaching us new things about physics that we thought we already knew. And that came for me later. That came in like 2015, discovering some new relation of the lower bound on the energy density of matter from playing with gravity. Now, you're also asking, well, what do we exactly do? I deliberately skipped over that because it is a little bit hard to explain. But I will try to explain it in the following way. When Bekenstein guessed the generalized second law of thermodynamics, the reason that he guessed that the black holes have an entropy proportional to their area is that in this funny interplay of how different people work, in 1971, Hawking had proven that the area of a black hole can classically only ever increase. It cannot decrease, roughly because you can't throw negative mass into it. And that's what you'd have to do to decrease it. It's more complicated than that, which is why it was a quite celebrated theorem. But that made the area a good thing to sort of guess, right? I mean, stuff that only goes up sounds like entropy. Remarkably, when Hawking finally discovered that black holes evaporate and that their area actually decreases, so the area theorem is actually wrong. Why is it wrong? Because things fundamentally don't need to have positive mass. They can have negative mass, and there's always a bit of negative energy in the neighborhood of a black hole, it turns out. Nevertheless, the generalized second law of Bekenstein survives in this setting which hadn't been discovered when Bekenstein guessed his generalized second. Bekenstein was worried about teacups going into black holes, not radiation coming out of it. But when you calculate the entropy of the radiation coming out of the black hole, it more than compensates for the decreased area of the event horizon. So again, the entropy overall goes up, and the generalized second law works. Okay? So the way you can make a living in theoretical physics is if you take other theorems that involve somehow the area of something from a GR textbook and replace the area with area plus entropy outside of it, very roughly speaking, and hope that that gives you something that's actually true. All the theorems in classical general relativity involve assumptions about matter not having negative energy density. Okay, so they're all really kind of wrong. Right? And so you can hope, and that was the gamble we took, that if you replace the area by this sort of quantum corrected area plus entropy of the matter outside of it, that you get, more or less word for word in the theorem about the area, that you get something that might actually be true in nature. Hope for the best, right? And we did this for the dumbest possible thing. There's a theorem called the focusing theorem in general relativity, which says that if you have light waves which say are parallel to each other and they encounter matter, like think of them as X-rays, you just go through it. But the matter will bend the light. You may have heard of this famous experiment, like bending of the light by the sun. So if the light rays initially aren't focusing, they will now be focusing towards each other. They're going towards each other. They never do that. Well, except if there's negative energy density. Then they actually do that. And so we thought, hey, why don't we try a quantum corrected focusing theorem? We'll just write it down, we'll make it up and hope it works. Might actually be true. And, it was a guess. The guess could have been wrong. It could still be wrong, by the way. But we found that it implies a lot of other things that we knew already to be true. We tried to kill it by finding counterexamples, and there was a conspiracy, and it seems to always be protected by something. And most importantly, it implied, in 2 lines of algebra, this completely new result in quantum field theory that nobody had ever found before, and that took like 100 pages to prove. That doesn't mean it's right, but it makes us feel like we're on the right track. But it's that sort of thing where ultimately it's guess. If you want to discover a new law of nature, you're going to have to guess. And if we could just derive it from the old stuff, we'd already be done. So there's a bit of a dark art to the guesses you make. Yeah.
You're doing such a great job of making difficult concepts somewhat understandable. So
Thank you.
I heard Lenny Susskind once asked, why can't the second law of thermodynamics be wrong? And he said, well, it can't. Physics would fall apart. And then he went on to something else, and I went, I wish he had said a little bit more than that. So could you say a little bit more than, oh, physics would fall apart?
Well, there are these famous quotes, like, I don't know if I can, it was maybe Eddington or something saying that, you know, if your theory conflicts with experiment, don't worry about it. Experimentalists probably made a mistake. And then it goes on, there are a couple lines, and then, but if your theory conflicts with the second law of thermodynamics, you should go home in utmost shame or something like that. Never show your face again. Why is that? Well, I think it's, it has to do with the fact that the second law is really just a statistical statement that is sort of a mathematical necessity. I try to allude to it with my example of the air collecting in the corner of the room. We know why that's not going to happen, and it's not because it can't happen, it's because it's so unlikely. It's that there are so few states comparatively corresponding to all the air being in the corner of the room and the air being filling up the room by, you know, orders of magnitude that are completely unimaginable. And so it would almost imply a sort of inconsistency of math, or yeah.
So I don't know if this is a semantic problem or that I'm having, but to go from theory to practice, how, based in sort of fumes and fantasy conspiracy, are companies like Qubit or Rigetti in Berkeley in terms of using some of the theory you're talking about?
Oh, thanks for that question. So, theory and practice, and you're asking about quantum computing companies. And I should have said this actually. So, quantum computing it's a real thing. And it's a technology that is basically taking the insane craziness of quantum mechanics and building machines with that craziness. And it's hard because you have to thread the needle, and I mean technologically it's hard, because I just told you that for large objects quantum mechanics likes to hide itself because, you know, they tend to interact with an environment. But you want to have a lot of bits that are quantum mechanical, not just 1 or 2, and so you have to protect them from that environment. And yet at the same time, you've got to be able to talk to them, give them input and read out some output and so on, and make sure they talk to each other in exactly the ways you want them to, which is why it's a challenging technology. And for this reason, so far quantum computers are pretty useless. They haven't yet done anything for us that, you know, we care about, that couldn't have been done by a classical computer 10 times better. But conceptually, the technology is, I mean, the ceiling is enormous, right? It is enormously high, and it could revolutionize computing and, you know, make it possible to no longer send secure money and so on. It will be a problem. But in the meantime, while we have these crappy machines, people need ways of testing them, of seeing what they can do with them, problems that they can solve with them that maybe aren't as important as some of these technological applications we have in mind for the future. And it turned out that we little quantum gravity people working on this abstruse problem of you know, bringing together these fundamental theories in physics tend to be really good at generating good problems for the quantum computer people. And so in fact, I lead a consortium that involves 3 experimentalists at Duke and at Stanford, and a bunch of condensed matter theorists over the US, and mostly people at Berkeley actually, studying quantum gravity. And the purpose of this consortium, which has been operating since 2018, has been to make these groups talk to each other and and facilitate the exchange of ideas. And it's been successful. To be honest, I didn't really think this was necessarily going to work. And it worked beyond my wildest expectations. And it's such a wonderful thing for me. Like, it's the first era in my career where I regularly talk to experimentalists. It's so wonderful, and it's like such great detox. You know, if you're like these people, like it. No, it really, it even if, you know, I don't think we're gonna, you know, solve quantum gravity by asking somebody with a quantum computer to do this or that. Just culturally, I think it's actually nice to be forced to think in terms of like, well, how would you do this with a machine? You know, and concepts such as quantum error correction, which were thought to be technologically relevant for building a quantum computer, have turned out to play an enormously important role in how apparently quantum gravity encodes space-time. It's a quantum error correcting code. There are concepts from quantum communication, fairly abstruse concepts that I'd never heard of before, that have entered the catalog of like how we think space-time actually emerges from a quantum theory. So it's fortunate for us that this technology is emerging together, you know, with this moment where we're realizing that gravity knows about quantum mechanics, and we've been using that extensively.
Wait, hold on for just a second. I'm sorry, forgive me for this, but I know that Hopmonk likes to close at 9 p.m. Don't worry, the doors will not be bolted, but I understand that we owe them something. They've been so nice to host us here. Maybe after one more question, maybe Raphael would hang around for a few minutes, even perhaps after 9, to answer questions individually. Yeah? Let's take maybe one more question.
Sure.
Well, we know that a moving electric charge will generate electromagnetic wave. What generates or can generate a gravitational wave? Second part of the question: if there are gravitational waves, what about any possible wave-particle duality? In other words, are there gravitons?
Yes and yes. So, in the case of electromagnetic wave, it's not enough for a charge to be moving; it has to be accelerating. But yeah, then it'll emit electromagnetic waves. And similar for mass. So for gravity, the role of the charge is played by the mass of the object. And it's a little bit harder to emit gravitational waves. But for example, if you have like the Earth just going around the sun is actually emitting gravitational waves. Not an appreciable amount. It's not a lot. But the gravitational waves that we observe, and there was this great breakthrough a few years ago by LIGO observing gravitational waves, they come from extremely powerful sources where you have, say, two black holes that are spinning around each other, and they're spinning ever more closely because they're emitting gravitational waves. And then when they finally collapse into each other and form a bigger black hole, that is an event that emits like a gigantic amount, like some fraction of the mass of these black holes is some appreciable fraction is converted into gravitational waves, and those are the ones we see. Those are like classical electromagnetic waves. They're not very quantum. In some sense, there's like an insane number of quanta sort of stacked up on each other, and so they don't behave in a very quantum way. It's like radio waves when you listen to the radio. But fundamentally, yes, we think that small ripples, that ultimately gravitational waves are also quantized the way that light particles are, and we call them gravitons as opposed to photons.
Please thank yourselves, Wondernauts, for being here, Hopmonk for hosting us, and most of all, Dr. Raphael Bousso for talking. For teaching us. Thank you.